Please share your screen if you are ready.
Can you hear me?
Mm-hmm.
Okay. So can you see the screen?
Yep, we can see the screen. It looks great. And we'll give you 15 minutes from when you start. We're just 3 minutes behind schedule. It's fine.
Okay, so let me begin. So today I will discuss relation between the lowest Landau level limits to the higher rank symmetry and the works based on my paper with collaborator here. So let's consider the 2D electron in magnetic field with this simple Lagrangian. And the D here are nothing but the covariant derivative. And here we also introduce the G factor that describes the interaction of the electron with the magnetic field here. And when G equal to 2, we can rewrite this Lagrangian with this form. So if you see that from this equation, if you integrate out chi, you will come back to the previous Lagrangian when G equal to 2. And in the fractional quantum Hall, you have the distance between the Landau level. Of course, you know that with the gap equal to magnetic field divided by mass. So the lowest Landau level limit can be taken by text the m go to 0 limits. In this case, you zoom in on a single Landau level and forget about the higher Landau level. And from this, from the new Lagrangian, when you take the massless limit, you can just simply ignore this term. And from this point of view, you see that the two new field Dagger now are Lagrangian multiplier that impose the lowest Landau level constraint. So dz bar icon per psi equal to dz icon per psi dagger and equal to 0. So it's simple from this point of view. So the lowest Landau level Lagrangian has some global symmetry that are consistent with the lowest Landau level constraint. So of course, you know the global U1 transformation give us the conservation of total charge. Furthermore, you also have the global magnetic translation here when the electron field transform in this way. Okay. For Z is nothing but the X plus IY that I forget to introduce. And L here is nothing but its magnetic length. So you can show that this transformation satisfies the lowest Landau level constraint when per psi pi Z also satisfies the lowest Landau level constraint conditions that I introduced in the previous slide. And from this global magnetic translation, you have the total conservation of the total dipole moment in the lowest Landau level. To derive this equation, again, you need to use the lowest Landau level constraint on the electron field. And we also have the global magnetic rotation, where you do nothing but it just rotate the coordinate. And from the global magnetic rotation, you have the conservation of total angular momentum in the lowest Landau level with this form. So again, to derive the angular momentum in the lowest Landau level, you again need to use the lowest Landau level constraint on the electron field. So when you combine the three symmetry, we have the conservation law and we have the conserved global charge with this form. So we have the conserve of total charge, conserve of dipole in X and Y direction, and you also have the conserve of the trace path of the quadrupole. So rho here is the charge density in terms of per psi dagger per psi. So you see that we have the same conserved global charge in the chairless symmetric tensor gauge theory introduced by Predko. So you see that the lowest Landau level somehow has the same conservation law as the symmetric chairless tensor gauge theory. Now I can also derive the Ward identity. So for the electron in the magnetic field, you have the following conservations: the local conservation of the charge is the charge conservation equation, and the second equation is nothing but it's momentum conservation. And because of the magnetic field, you have the Lorentz force, and the momentum density defined in terms of the current density, which is multiplied by the mass. And in the massless limit, again, we see that this equation is nothing but it's a force balance equation where you can derive the current in terms of the stress tensor. And then we see that if we define the symmetric tensor current in terms of stress tensor with this form, and from this explicit form, you see that the symmetric tensor current is changeless. And then you plug back to the charge conservation from the current in terms of stress tensor, you have the final form here. It's nothing but it's the Ward identity of the changeless symmetric tensor gauge theory introduced by Pretko. So I show you the global conservation and the local Ward identity that's identical with the changeless symmetric tensor gauge theory. So that's implies that the lowest Landau level somehow has the symmetric changeless tensor gauge symmetry. So let me explain like explicitly how to get it. So here I consider the deep transformation in the Newton transformalism introduced by Sun with this form. So here is the transformation of the gauge field, ISO and AI, and also the metric with the deep transformation. And again, in the massless limit, we ignore the last term, the lowest Landau level limit. And of course, you also know the gauge transformation, a mu transform this way. We find here the parameter of the gauge transformation. So in the constant background magnetic field, we choose the symmetric gauge, so that the AI have this form, explicitly have this form, where L is again magnetic length. So if we choose an area preserving deep and a compensate U1 gauge field, so with the deep parameter with this form, so with the explicit form here depend on the function lambda. Yeah, this explicit form satisfies the area preserving condition. And we also choose the gauge transformation that depend on also the lambda. So with these two parameters of the deep transformation and gauge transformation, we see that we have the gauge transformation of nonlinear higher rank symmetry, where the AI doesn't change, but A naught and Gij change with this form. So this transformation look complicated, but let me linearize it and you see the very familiar equation. So let me first define the changeless symmetric tensor gauge Aij in terms of Gij with this form. Okay. And so the linearized version of this nonlinear higher rank transformation actually has this form. Okay, let's say lambda is a parameter depending on space and time. And you see that this linearized version is nothing but the gauge transformation of changeless symmetric tensor gauge introduced by Pretko in 2017. So I think that at this point, I convinced you that the lowest Landau level limit of the electromagnetic field has the symmetric tensor, the changeless, the gauge symmetry of the symmetric tensor gauge, the changeless symmetric tensor gauge. So from this gauge transformation, of course, we can define the very invariant field strength. So here is the symmetric tensor electric field and symmetric tensor magnetic field. So of course the linearized version, so let me consider the consequence of this high rank symmetry. So the linearized version of the high rank symmetry, we recover again the Ward identity here, with Jij defined through the stress tensor in the same way that we defined before. Furthermore, because of the gauge transformation, the high rank gauge transformation, we have the explicit form of the Gauge invariant Chern-Simons term in the higher rank symmetry have this form. So now, if we rewrite the higher rank magnetic field and the Aij in terms of the matrix through the previous definition, we see that this Chern-Simons term here is nothing but it's a Wenzi term in fractional quantum Hall. And so the first term will give you the Wenzi shift, and the second term will give you the whole viscosity. So basically, the higher rank symmetry provides the relation between the Wenzi shift and the whole viscosity. So, and sorry. The nonlinear version of the high rank symmetry as the area preserving depth satisfies the following commutation relation. So lambda here is the parameter of the gauge transformation that we introduced previously. And the bracket here defined explicitly by this form. And you can derive this equation in many different ways, but we see that this commutation relation satisfies this form. And we know that the operator that induce the higher rank gauge transformation is Q lambda. And so the commutation of Q lambda with any operator is nothing but it's a gauge transformation of this parameter with the parameter lambda. So from this definition of Q and the commutation relation, we have the commutation relation of the charge density. So this equation and this equation are just identical. And if we use the lambda 1 equal to exponential of ikx and lambda 2 equal to exponential iqy here, this commutation relation gives us the lowest, the leading order in of the GMP algebra. The commutation relation of the charge density satisfies this form. So basically, the nonlinear higher rank symmetry implies the lowest Landau the GMP algebra, which is a property of the lowest Landau level. So we see that the lowest Landau level enjoys this higher rank gauge symmetry. Then basically we can think of the fractonic behavior of the excitation in the lowest Landau level. For example, the charge excitation like quasi-particle and quasi-hole in filling fraction 1/3, for example, the gap state. You see that both of them are fractal because it's the charge, the fracton of the charge excitation, and because of the symmetric tensor gauge symmetry, they are fractal. And also the other excitation, neutral excitation, which are the composite fermion when the filling fraction equal to 1/2, 1/4, and theta, 1/2n. And this composite fermion is a charge neutral, and it has a dipole moment. And because of the Challis part of the Challis condition of the symmetric tensor gauge symmetry, the dipole moment can only move in the direction perpendicular to the dipole moment. And so basically the composite fermion can only move in the perpendicular to this dipole moment. And the same picture was introduced independently by me and my collaborator in other publication. In the fractional quantum Hall, we have another neutral excitation, which is magnetoroton excitation, introduced by Gervin, McDonald, and Plattman in 1986. And Holden suggests that this neutral excitation is spin 2 mode. And in my other paper with Gokai and Cern so show that this excitation in the long wavelength limit is a current gap spin 2 excitation, and it is a massive graviton in the fractional quantum Hall. And in a very interesting paper by Sochen Zhang in 1992, it suggests that the long wavelength version of the magnetoroton is a quadrupole. And so basically, we can come back to the symmetric tensor gauge symmetry. We see that the dipole can only move to the perpendicular to its dipole moment, but the quadrupole can move freely. So basically, we see that different type of excitation in fractional quantum Hall shows the fractonic behavior due to the symmetry in the lowest Landau level. Okay, Andre, are you here? I give you a present, and this is a biometric theory for PS5. So instead of the background matrix, we define the immersion dynamical matrix with this form. So the GIJ is the dynamical matrix defined in terms of immersion view by. And here is now the linearized version of this definition. And from the immersion dynamical matrix, we can define the immersion dynamical tensor gaze AHIJ defined in terms of GHIJ. So from that, we can follow from our previous formalism, define the immersion dynamical Chain-list symmetric tensor electric field with this form. Okay. So here, instead of the AIJ defined in terms of background matrix GIJ, we define the AH GIJ defined in terms of immersion matrix GIJ. And here is my proposal for the biometric version of PS5. So the first two terms is well known. Is the one here because of the shape of the PS5. When the shape of PS5 go to 1. And now we concentrate in this term is the E square term. So this term, because of in the definition of E hat, you have the background A naught, and basically this term will contribute to the density correlation. So in the previous version, the biometric theory introduced by Andre and Son, the two components of current immersion matrix Q and Q bar here are canonical conjugate because of the term Q dt Q bar in the Lagrangian. So from this equation, so from this time, you see that Q and Q bar are canonical conjugate. However, in the new Lagrangian that we propose here, Q and Q bar are independent spin 2 mode. Because you see that E square has this form. So in this equation, you see that Q and Q bar are not conjugate of each other anymore. And from this equation, we expect that we have two massive gravitons. So to Q and Q bar are two current spin 2 mode, two independent current spin 2 mode. And because of the particle Hall symmetry, they have the same dispersion relation. And we expect to verify the appearance of two spin 2 mode in experiment and also in numeric. Okay, so let me come to my conclusion. So there's many things that I didn't have time to talk. I don't have time to talk. So first of all, we also have the 3+1 version of the area preserving and also related to the higher rank symmetry. And this 3+1 version will implies the multiple conservation of the skyrmion in an antiferromagnet. And in the talk, I saw that the high rank symmetry is nothing but is lowest Landau level limit symmetry in the fractional quantum Hall. And from this, I saw that excitation in fractional quantum Hall basically has a fractonic behavior as a consequence of the high rank symmetry. And now I saw that's the relation between the fractal quadrupole and the magnetotone, which is a massive graviton in fractional quantum Hall. And let me thank Sergey and Andre for discussion. Thank you.
Great, thank you. Thanks.